Go ahead whenever you're ready.
Thank you. I am also a visitor, so so I'm a visitor in iTHEMS and at the Region Quantum Computing Center. My main affiliation is Quantinuum, a quantum computing company, and my name is Enrico Rinaldi, and I will be giving the coffee meeting talk today. Let's see. Everybody's here to hear this talk. And you all know this is about the Nobel Prize in Physics in 2024. And I'm gonna keep it short, but also probably interesting. Let me ask you, who here is a physicist? Oh, okay, good. Who here is a neuroscientist? Okay, good. Well, all physicists are neuroscientists, and all neuroscientists are physicists, and everybody is a computer scientist. So that's the meaning of this Nobel Prize in Physics. There are a lot of connections between physics, computer science, neural networks, the brain, and actually, I think it's a very good thing to be here in iTHEMS because that's what the I in iTHEMS stands for. It's an interdisciplinary center. And with this Nobel Prize in Physics, the Nobel Committee was telling us that neural networks, or NN, or AI, or whatever you want to call it, is interconnected with physical systems. But neural networks, or artificial neural networks, they came about because people wanted to understand the brain. So this is also tightly connected with biological systems, which, of course, are physical systems. So this Nobel Prize in Physics is really a nice starting point for me to tell you about the connections between artificial neural networks, neuroscience, and physics. So what is the Nobel Prize in Physics about? It's about awarding two scientists. One is an American scientist, John Hopfield, and this is probably related to the options that Atsuda-san mentioned. John Hopfield is a physicist, graduated in physics, studied physics for a long time, in particular quantum matter, and then also moved to neuroscience and trying to use physics to understand how the brain works. And the second awardee is Geoffrey Hinton, British-Canadian computer scientist, not a physicist by training. And Hinton got his PhD from Edinburgh, where I got my PhD. So never met him. Of course, he's much older than me, but we have two awardees getting a prize shared 50-50 for their work in artificial neural networks and the discoveries they did around the 1980s, which was where I was born. Ish. I'm not telling how old I am. So, what did they do that deserved the Nobel Prize in Physics? So, I'm going to describe first what John Hopfield did when he formulated a theory of an associative memory. It's let's call it a computational device that can retain memory. And if you give to this device some corrupted data, it will retrieve for you the closest data that it has about the memory that you have encoded in this computational device. So in practice, what he was doing was associative memory. Was trying to understand how the brain works and what kind of things you need to have in the brain in order to have memory. And of course, he was a physicist. So he said, okay, let me start easy. Let me start with fundamental constituents. Let me start with interactions between constituents. And he just came up with a network, what we today call a neural network, artificial neural network, recurrent artificial neural network. These are all words that just mean I have a bunch of components. They are connected together. They can be all-to-all connected, or you can just have some of these connections be zero and so on. And each of these components is very, very simple. It's a bit. It's 0 or 1, or +1 or -1. Just two numbers. Okay. And these connections are some weights, some numbers that you can fix yourself to create a memory of some pattern. So what do I mean by memory of a pattern? What is a pattern? A pattern here, or a state of this network, is the collection of these variables here, Si. So I have S1, S2, S3, Sn. If I specify a list of +1, -1, -1, +1, this is a state, okay? And the memory that is encoded into this network is one specific state that has the minimal energy. So here, memory is associated to energy. So Hopfield came up with the concept of energy for this type of artificial neural network. But it shouldn't sound too strange, because this type of system is something we actually have in physics, and people have studied many years before the 80s, okay? And to be honest, this type of network was also studied in Japan before Hopfield, with a very similar conclusion in the 60s. So the idea is that these connections and the values between at the nodes of an edge tell me how much energy there is in this configuration or in this state. And if I assume that this guy is 1 or positive, let's say, then these two values here will want to be pointing in the same direction, both +1 or both -1. If this value is negative, then they want to be pointing in opposite direction, +1 and -1, or vice versa. Okay. So I'm assigning the concept of energy. I can do it for a link, or I can do it for the entire network by summing up all these numbers called weights. You might have heard about the weights of a neural network, and the values on these things here. So this is the equivalent of an energy. And I want to make this, well, I can put the minus sign if I want to minimize this energy, but this is the energy of a configuration of a state. And again, I said a memory in this case is the configuration that gives me the lowest energy. So if I have this W fixed, some values, then I will just have to flip these S values in order to get to the smallest energy. And surprise, the state that I get is exactly the state that the network has memorized. Okay, so do you see something missing here? The missing part here is, how do I select this W in order to have a specific configuration? So that was part of the work that Hopfield did. So the goal was to have a landscape of energies like this, where this is energy. And this axis here is the axis of my states, S, or collection of variables, S. And as I change S, as I change collectively all these variables, I want to be able to get to a point where this energy is the smallest for some S star. Okay, so that is done by just adjusting this weight here. When do we get the smallest energy here? We get the smallest energy, again, as I said, if I have two of these pointing opposite direction, I should have a negative number here, -1. If I have these two pointing in the same direction, I should have +1 there. So I'm selecting the W's by finding the configuration of minimal energy. And once I know those W's, my network now has encoded a memory and will be able to retrieve that memory by simply updating these variables on the nodes. So this is the work of John Hopfield, and this really started the entire field of learning using a machine, or having a machine learning something. In this case, learning a pattern of plus and minus ones. Pretty simple, but at the time, very, very difficult to do. And here, the concept that he used to make this work was a concept from physics. He was a physicist. He used the energy of a spin system. So tools that were already available from physics ported into the field of neuroscience, however you want to call it. So this is the first connection between physics and neural network. So you might think that this is very far from the neural networks that we are using today, and that is true. So I'm going to now tell you what Hinton did and why he was awarded the Nobel Prize. Because what Hinton did is very relevant for today's generative AI tools. In particular, he designed a way to transform this type of network into something that could also generate new things. Okay, a mechanism to start from here and having a probabilistic way or stochastic way of sampling new patterns, new configurations. Okay. Is there any questions so far? Probably. Yes.
So to this point, what is the advantage of storing the weights rather than the state? Because there are more weights than elements of the state, so it would be cheaper to memorize.
The network only has the weights. So the network starts with the weights. Then these nodes, they can be something that you input. And then there is an update rule that tells you how to go from what you input to the memory that is stored in the weights. Was that your question? You don't store these guys here, you store the weights.
Yeah, my question is, what is the advantage? If I'm after some sort of memory, then it would be much easier to memorize the state I'm after, because that's whatever dimensionality of the system anyways.
You actually want a mechanism to recover that memory. So not just a way to store it. You want a mechanism to recover it. And that is what this gives you. In this associative type of memory. Associative means that you see something and you associate the memory that is closer to that thing you see. So in other words, you can think of this SI as your input or your data from which you want to associate a memory. And the memory is already stored in this network of weights. So the computational device is the network, and given a data as input, it will tell you after some procedure, which is the way to update these guys based on the weights, it will tell you what the memory is. Okay. So here,
Can I add to that? I think the part of it is also you're not memorizing one memory using the network, right? The idea is that you memorize a whole bunch of things and then you can retrieve any of them. So if you're trying to measure a lot of things,
in this case,
then,
one, but yeah.
right, but then the network can hold more than your states.
So good point. So how many of these memories can you encode in an Hopfield network that has n neurons? Well, it turned out, again, using physics and the tools from spin glass physics and what Giorgio Parisi got the Nobel Prize for in physics, again, if you have n of this, then the capacity of the memory capacity of this network is approximately 0.15 times n. So it increases with the number of neurons, but it doesn't increase very fast. So you can encode, if you have n equal 100 neurons, you can encode about 15 different memories using one set of weights.
So does that correspond to the number of MEMA?
Yes. In this type of associative memory picture, you can have multiple minima. They have to be uncorrelated, disjointed, and so on. And that's why this is limiting the capacity. So in some sense, you are going to get here if you start around here, or here, or here, or here. So they should probably all be at the same height, with the same probability, but I haven't introduced the probability yet. So
Would you have a degeneracy?
yes.
So the degeneracy maximize like you say 0.
So it can
Yeah,
happen.
I'm
also
sorry,
has-
we're not supposed to take questions, so that it's supposed to take only 15 minutes. So is it possible to hold the question until the end?
And then what happens after 15 minutes? How many minutes of questions?
Okay, well, I guess you want to take this question, but I mean, yeah, so it's
I'm
been
gonna-
15. Yeah, so go ahead.
Go ahead. Yes. Okay. So what Hinton did was to introduce elements of statistical mechanics to this system. So before we just had an energy of some configuration. Now that energy comes with a probability. Or in other words, the probability of this configuration, P of S, will depend on the energy of the network. And it will depend in a way that's proportional to the energy with some temperature parameter. And this idea comes straight from statistical mechanics and from the Boltzmann distribution. That is why the network that Hinton creates based on Hopfield setup is called a Boltzmann machine. Now you can see even better why they were awarded the Nobel Prize in physics, right? They just did physics. Now it happens to be useful for neural networks, but it's physics. You take a physical system of spins up and down with interactions, Wij. Each configuration is weighted by the energy given by some temperature. So you have thermal fluctuations that can affect how these nodes flipped from +1 to -1. But they use this to learn something. For example, in the case of the Boltzmann machine, what the Boltzmann machine can do is it can learn the distribution of a data set. So instead of just encoding one memory or two memories or three memories or 0.15 n memories, now the Boltzmann machine encodes an entire distribution of your data. So you pass the data to your network, the network learns how the data is distributed, and then can spit out samples from this distribution according to the weights that it has learned. This is the basis of generative AI, which is what ChatGPT is doing, Claude, Mistral, Llama, all these large language models that are helping you writing your papers and doing your research are based on the idea of sampling from a probability distribution after having learned that probability distribution from data. And that is really what is the big breakthrough in the Boltzmann machine from Geoffrey Hinton. I want to take questions, Catherine. So I'll stop here. And thank you very much for listening.
Thank you very much. So are there any questions?
The temperature here is a parameter that you can tune in order to affect how a configuration is sampled. So it affects the probability that a configuration has. So in this case, it can be absorbed in the weight, but it's a parameter. Yeah. It's not physical temperature when you talk about neural networks, but it's a parameter of the distribution, the probability distribution of a configuration.
So what's the extreme limit, like an infinity and a zero temperature?
So in the zero temperature limit, this guy becomes the Hopfield network. It's all deterministic. There's only the minimum. There's no thermal fluctuations. So if you start from one thing, you get down to the minimal energy state, and that's it. You don't move from there. Here, you can actually, if you have a temperature, you can jump out of the global minimum and explore some other regions of the configuration space.
So infinity just equal everyone, if we say just equal.
You know?
Yeah, related to this question, if there is a temperature, I guess there should be a corresponding heat mass. So in this case, is there any counterpart of the heat mass?
In terms of, in the case of the neural network, Boltzmann machine? No.
But I guess it should be related to kind of a second law of thermodynamics. In my opinion, it should be connected to the kind of the learning dynamics. So that's so
Right. So as I said, you can take this and put it into the weights of your so it's part of, if you want, if you're learning those weights, then it becomes part of the learning process. You're right. Yes.
Is it kind of statistical mechanics?
Yes.
What do they use as a mathematical tool?
The same as statistical mechanics, equal, the same, exactly the same. Yeah, it's all physics. Yes.
Yeah. So, could you explain how this discovery related to what you are doing now?
What I'm doing now. Okay. I am using neural networks to help me discover new physics or learn about physics. So I'm not using physics to learn about neural networks. I'm using neural networks to help me doing physics. So that's what I'm doing. So maybe I can get the Nobel Prize in computer science.
When?
Well, there isn't a Nobel Prize for computer science. So I guess that's also why a computer scientist was able to get the Nobel Prize in physics. Thank you.
Okay, my question related to in this case, you use the kind of distribution function for canonical ensemble. But in classical mechanics, we have another like microcanonical or grand canonical. Is there any possibility to use that microcanonical or the canonical to analyze the neural network?
Yes, I think so. Yeah, I think you can do it in the microcanonical. Use the density of state.
I think grand canonical is useful to understand, let's say, the assumption in the state to equilibrium. Let's say another constraint, for example, the basic example. yeah, I still have no idea. Yeah, such kind of knowledge. Yeah.
So in general, I think this Nobel Prize in Physics is teaching us that we can take physics and apply it to anything.
Okay.
Yeah, that's great. So you can take your preferred statistical mechanics tool and try and use it for understanding traffic or networks of people, like Jason is doing at LinkedIn, or these companies that have a lot of data try to do. They, if they want to understand things, they often resort to physics, because physics is a way to explain how things work from first principle.
Okay. Well, thank you very much.
So what's the entropy here? You can calculate entropy. So what's the meaning of entropy?
What's the meaning of entropy?
Yeah.
In this case, it's you're counting, the number of configurations that you can have. So it depends on the distribution of the data. It's a property of the distribution of the data that you're learning. So you can have a high entropy distribution or a low entropy distribution. Okay. Thank you very much.
Are there any more questions on Zoom? No.
Online?
And I'm sorry, is there one more question in the common room, or did I heard somebody talking?
Yeah, I was asking if there were questions online.
Yeah, there does not appear to be any. So far, nobody has come forward. So I think maybe that's it. So let's thank our speaker one more time. And of course, Enrico is there in person, so you can feel free to ask him more questions. Thank you very much.